Hello and welcome to this FP3 exam paper walkthrough. This was the June 2024 paper. You were allowed a calculator and the formula booklet. Question 1. The hyperbola h has foci with coordinates this. Remember that the foci have coordinates a, e, and directrices this. And again, remember that the directrices are plus or minus a over e, eccentricity e. Determine the value of e. We can do that with the information we've been given by setting up equations. 13 over 2 must equal ae, and 72 over 13 must equal a over e. So a is equal to 72e over 13, and we put that in the equation above it. 13 over 2 is equal to 72e squared over 13. That gives us 169 over 144 is equal to e squared. Therefore e is 13 over 12. Part B. Determine an equation for h, giving your answer in the form this, where p, q and r are integers. That'll help me check at the end if it looks correct. That's part A. Part B, and the first thing down here, I'm going to find the value of a, because we know a is 72e over 13, and we now know e. That's 72 over 13 times 13 over 12. That gives us 6. To get the equation of the hyperbola, I also need b, and in your formula booklet, if you forget either of these here, this one and this one, these are both in the formula booklet. And this equation is also in the formula booklet. E squared minus 1 times a squared gives you b squared. So 36. 169 over 144 minus 1. All of that equals 25 over 4 for b squared. So b is 5 over 2. Then we can put that into our general equation for a hyperbola, which is this. Also in the formula booklet, if you forget any of these things, they're all there. Y squared over 25 over 4. And we're going to multiply by those denominators, which gives us a 900 on this side. 25x squared minus 144y squared. So p is equal to 25, q is equal to 144, and r is equal to 900. Moving on to question 2. Given that m has exactly two distinct eigenvalues, lambda 1 and lambda 2, where lambda 1 is less than lambda 2, determine a normalized eigenvector corresponding to the eigenvalue lambda 1, the lower of the two. We don't have any clues to start us off here, we're just going to go through and find all three, and a good check will be that two of them should be the same. To do that, we want the determinant of a minus lambda I, or maybe I should say m in this case, and that will have to equal 0. That will give us the value of lambda. So we've got 2 minus lambda, 0, 3, 0 minus 4 minus lambda, minus 3, 0 minus 4, and minus lambda. The determinant of this, the first element multiplied by its minor, which is a minus 4 minus lambda times minus lambda. If I quickly factorize that minus there, we see that all of these become positive. So we get lambda 4 plus lambda minus 3 times minus 4. And then the second term is 0, because the second element of the top row is 0. And then the third element, 3 on the top row, times by its minor, but that is a 0 minus 0. So we get just the one term here, 2 minus lambda, 4 lambda plus lambda squared minus 12, I don't like that, lambda squared plus 4 lambda, there we go, and that can factorize. We get plus 6 and minus 2, although they look a little different there, and that gives us lambda is equal to 2 twice, and is equal to minus 6 once. Oh no, let me be careful here. They've said lambda 1 is less than lambda 2, so that's the equal sign there anyway, but that should be a 2, and this one is the lower value, minus 6. So I've got the three eigenvalues. Now we need a normalized eigenvector corresponding to the eigenvalue minus 6. So we've got 2, 0, 3, 0, minus 4, minus 3, 0, minus 4, and 0. And the whole idea of an eigenvalue is that the vector is equal to the eigenvalue times that same vector. So on the left we've got 2x plus 0y plus 3z as our first element, and that has to equal minus 6x on the right, the first element. Then our second row, we've got 0x minus 4y minus 3z, and that has to equal minus 6y on the right. And then finally, the easiest one perhaps, 0x minus 4y plus 0z has to equal minus 6z. I can rearrange this one to give 2y equals 3z, and that helps me see that that's actually the same as that one there, giving me the same information. So I'll rearrange this one as well. That gets me 8x is equal to minus 3z. So I've got these two conditions here, and so long as these two conditions are true, I can choose any numbers I like. I think the easiest way to do this would be to make z an 8, because then x, when I put the z in here as an 8, I get a whole number out of that, minus 3. So let z equal 8, then x is equal to minus 3, and because of the 2 here, that will give me a whole number down here as well. Y will equal 12. You don't have to choose these numbers, but I always like to have whole numbers if I can. Minus 3, 12, 8 is an eigenvector, and you can have any multiple of that, but the question actually wanted a normalized eigenvector. So what we then do, 3 squared plus 12 squared plus 8 squared, divide all three components by that. That is the unpleasant number square root of 217. So although that's a not very nice number, I don't think there's been anything tricksy about this question, so I'm still fairly confident, unless I've made a silly mistake in the algebra. So we divide that, we get minus 3 over root 217, 12 over root 217, and 8 over root 217, and that is our normalized eigenvector for the eigenvalue minus 6. Part B, the line L1 has equation this, where mu is a scalar parameter. The transformation t represented by m is transforming line L1 into line L2. So m is acting on L1 to give us L2. L1 is the one that we've got, so we're just applying our matrix directly onto the line equation given on the screen there. I'll write that as a single point, 4 plus 2 mu minus 1 and minus mu, and take that down with me. I've got them both here, m acting on the line, so that's 2 times 4 plus 2 mu is 8 plus 4 mu, plus 0 times minus 1 plus 3 times minus mu. Second row times the column, that's a 0 plus 4 plus 3 mu, and then 0 plus 4 plus 0, which is quite a nice set of numbers. And just put that back in the same format it had before. 1, 3, 0 mu, is that what they wanted? Determine a vector equation for L2, give me an answer in the form r cross b equals c. No, that's not at all what they wanted. So we've got r cross b equals a cross b, so I need to cross my two vectors to get the constant vector c. So b is just the direction vector that we've got there. That's 1, 3, 0. A is the point, 8, 4, 4, and B again is the direction vector 1, 3, 0. Cross those two, and we get 0 minus 12 for the first component. For the second one, 4 times 1 minus 0 times 8. And for the third component, 8 times 3 minus 1 times 4, 20. And this is just r cross 1, 3, 0. That should be the correct answer in the correct format, and I think we are finished. On to question number 3. We've been given y is equal to r sin root x squared minus 1. We need to prove the derivative is equal to that thing. Over to the formula booklet. This is the FP3 section. R sin here, the derivative is given as this. So that's there on the side, but that's for r sin x, not r sin the root of x squared minus 1. So I can put the root of x squared minus 1 into that expression. So it's 1 over square root of 1 plus root of x squared minus 1 squared. And then I need to remember to multiply by the derivative of x squared minus 1 to the half, and that differentiates to a half x squared minus 1 to the minus a half times by 2x. So I cancel those and drop the rest of it over here. That's x squared minus 1 to the minus a half times x, and then this square root inside a square root simplifies quite a lot. We get 1 plus x squared minus 1, square root of that just becomes x, which is good because that cancels with that and leaves us what we need on the top there. That all cancels with that, and we get 1 over square root of x squared minus 1. Having proven that, we now have f of x is equal to that fairly messy looking thing. Determine the exact values of x for which that equals 0. So that was all part A. Part B down here, we're switching to function notation. 1 over 3 r sin thing we just had minus arc tan x. Okay, straight away back to the formula booklet. This time arc tan, this one here. Okay, that's on the right there. So our third does affect this from part A, and then 1 over 1 plus x squared from the second term, and we need to set this equal to 0 and solve. So I'll bring that over here, 1 plus x squared, 1 over 3 root x squared minus 1. Bring them out of the denominators. Square everything. That gives us x to the 4 plus 2x squared plus 1 over here. 9x squared minus 1. 9x squared minus 9. Bring those over to keep my x to the 4 positive. Now I want to solve this. This is a quadratic in x squared. So x squared is equal to... I was going to use the formula and I've just realized it will factorize. Let's do that instead. X squared minus 5, x squared minus 2. So we get x squared is equal to 5, or x squared is equal to 2. So x is equal to plus or minus root 5. X is equal to plus or minus root 2. Go back and double check if there were any limits on x. Yes, x had to be greater than 1. So both the positive values are, but neither of the negative values. So we've got root 5, root 2. And I think that was the end of question 3. On to question number 4. Use the definitions of hyperbolic functions in terms of exponentials to show that this identity is true. Now this is one identity that I'm going to start on the right hand side, because there's going to be a lot more terms in there, and I think they're going to simplify to the left more easily than starting on the left and trying to build terms in to get to the right. Usually I just start with the left, but in this case, starting on the right with this, cosh A sinh B, putting in all of these, we've got e to the a minus e to the minus a over 2 times e to the b plus e to the minus b over 2 plus e to the a plus e to the minus a over 2 times e to the b minus e to the minus b over 2. Now it's just a case of simplifying everything. We're multiplying these, don't forget these have got brackets around them. So we've got e to the a plus b minus e to the b minus a plus e to the a minus b minus e to the minus a minus b. And all of that is over 4. Same idea over here. Brackets helps me do this. E to the a plus b plus e to the b minus a minus e to the a minus b minus e to the minus a minus b. And again, all over 4. Then when we put these two fractions together, this one and this one will cancel. This one and this one will cancel. And the other two pairs will add together. So we get 2 lots of e to the a plus b minus 2 lots of e to the minus, let me factorize this now as well, a plus b, all over 4, missing some equal signs here. Then we cancel our numbers, we get e to the a plus b minus e to the minus a plus b over 2, and that is the definition of sinh applied to a plus b, which is our left-hand side. Therefore we have proven this identity. On to part B. Hence, express this thing in the form this, where r is greater than 0, giving alpha in the form log p, where p is an integer. So we have to use what we've just done. So we're applying the identity onto this little bit here. So we want to expand out this with x and alpha. So r sinh x plus alpha is equal to r lots of, at the top of the screen there, sinh x cosh alpha plus r lots of cosh x sinh alpha. And the thing we're trying to express is 10 sinh x plus 8 cosh x. So comparing these two, we can see that 10 must equal r cosh alpha and 8 must equal r sinh alpha. Dividing through, r sinh alpha over r cosh alpha is equal to 8 over 10. Gets rid of the r's, and we get tanh alpha equals 4 over 5. Jumped across to the formula booklet again for this, because we're about to do an r tanh. So I've got that down on the right there. So alpha is equal to r tanh 4 over 5. So I'm going to put 4 over 5 in there. That gives me a half log 1 plus 4/5 over 1 minus 4/5. That gives me 9/5 over 1/5 is a 9. And we can bring that half in as a power because that's a root and turns it into a 3. Now I can drop that back into 10 equals r cosh alpha. There is a quicker way of finding r, but I'm going to go through the motions here using cosh. 3 plus 1/3 over 2, 5 over 3, that's 5/3 of r is 10, So r is 6. You could also have done r squared is equal to 10 squared minus 8 squared, and that's fine if you do it that way. You just have to remember that you're subtracting, not adding, as you would be if you were using trig rather than hyperbolic trig. So we've got 6 sinh x plus log 3. And is that going to match? Yes, alpha is log p, where p is an integer. So p is equal to 3. Next section, hence again, hence solve the equation this equals 18 root 7. So the thing we've just found, basically, we're going to equate to 18 root 7, giving an answer in this form here where q is a rational number. So the thing we finished with here, 6 sinh x plus log 3 is equal to 18 root 7. Dividing both sides by that 6. And then of course we're going to have an r sinh. Back to the formula booklet in just a second. Now it's this one I'm going to take across. So that gives me x plus log 3 is equal to the log of 3 root 7 plus the square root of 3 root 7 squared, 63 plus a 1, that's a nice number, 3 root 7 plus square root 64. But if we take that across, then we can put that into our log by dividing like so, and that gives us a root 7 plus 8 over 3. Log 7 plus a rational number where q is a rational number, yes. We got q is equal to 8 over 3. On to the next question. Here we've been given an identity with a p and a q, where p and q are integers. Determine the value of p and the value of q for 2 marks, probably 1 for each. They're not expecting a lot of process here. So we've got 4x squared plus 4x plus 17 is equal to 2x plus p squared plus q. Usually I would complete the square starting on the left, but because of that 2 in the brackets, which I wouldn't have if I were completing the square, I'm going to expand that instead. That gets me a 4x squared straight away, plus 2px plus another 2px. That's 4px plus p squared plus q, and then we can equate the 4p with the 4x here. That gives us, so that tells us that 4 is equal to 4p, p is equal to 1, and if p is a 1, p squared is also a 1, so q must be a 16 to make up the 17 total between these two. Okay, fairly easy start. Given that this equals that, where a and b are also integers, write down, this is going to be even less work, 2 values for 1 mark, the value of a and b. Oh yes, because all the denominators are the same, so we're literally just adding 1 to ax plus b to get 8x plus 5. So a is 8 and b is 4. An easy mark there. I'm a little bit worried about what's coming if they've got easy marks for the first 2 parts. Hence, use algebraic integration to show this, where k is a rational number to be determined. Okay, hence, of course, means use what we've just done. So they're expecting us to split this into 2 fractions and also use this probably somewhere in there. So we've got the integral of 8x plus 5 over 4x squared plus 4x plus 17 square rooted from 1/3 to 1. And the first thing we're going to do is split that into 1 over this thing plus 8x plus 4 over this thing. Actually, instead of writing that, let me put it as 2x plus 1 squared plus 4 squared, because I think that's going to be where we're headed with this, because we found that it's equal to 2x plus 1 squared plus 16 from part A. 2x plus 1 squared plus 16, which of course is 4 squared, and I'm doing that because I know this matches one of the formats in the formula booklet. 1/3 1, so jumping across to the formula book. The second term doesn't match any of these because of the x in the numerator, but the first term matches this one here, where a is 4. Okay, that very closely matches, but there is a linear transformation here. We don't have x squared, we've got 2x plus 1 squared, which does make a slight difference. If you were to put an ax in here, when you differentiated it, you would get an a multiplier, so that would be a 2 multiplier here. So if we're going backwards, we're integrating, we need a half. Hope that made sense. Our sinh of 2x plus 1, like that. And that's going from 1/3 to 1, but then we've still got this other part to go. That 8x plus 4 is close to, or certainly of the form, this thing here differentiated. So I wonder if I take 2x plus 1 squared, oh, maybe it's not so helpful writing it like that this time. Back to how we had before, 4x squared plus 4x plus 17. And if I put that in a bracket with a power half and differentiate that, I think from experience that will get me very close. We get a half of 4x squared plus 4x plus 17 to the power minus a half, which matches the denominator up there. And then you have to multiply by the derivative of the thing in the brackets, which is 8x plus 4. Oh, exactly. Except for the half. If I want to get rid of that half, I need a 2 there, which means I need a 2 in front here. So that's plus 2 lots of 4x squared plus 4x plus 17 to the power half. And I wasn't expecting to do that all in one row, so let me put that there like so. And all of this just off on the side there. And looking at this expression, I've just realized I must be missing an a somewhere out of this expression. Yes, sorry, that should be x over a, which means this over here should be over 4. Almost a disaster. That would not have got me the right answer at all. Now we need to put the limits in, trying to be a little bit more careful than I was just there. R sinh, when x is a 1, that gives me 3 over 4 plus 2 times 4 plus 4, 8, 17 is 25. Oh, 25, that's nice because that's going to be a square root. First one, minus half r sinh 5 over 3 over 4, and I'm leaving it like that because this is still the a when I change it into this format here. And this 5 over 3 will be the x, plus 2 lots of 1/3 squared is a 9th, 4/9 plus 4/3. Yeah, I've switched to my calculator. That tells me 169 over 9 to the power of a half, also a nice number for square rooting. Now I'm going to use the log format for the r sinh parts. That's a half log of x was 3, and 3 squared plus a squared, like this. Oh, there's a lot of nice numbers coming in here. It's well thought out. That's a 10 minus a half log of 5 over 3 plus root, grab my calculator again, 169 over 9 plus 2 lots of 13 over 3, 26 over 3. Sorry, minus. Tidying this up a bit, we get a half log 3 plus root 25, that's 8, minus a half log 18 over 3, that's a 6. Putting those constants together gives me 4 over 3. Then we pull a half out here, log of, combine these, 8 over 6 is 4 over 3, plus 4 over 3. Is that right? It looks good. K plus a half log k, where k is rational. K is equal to 4 over 3. Lots of opportunity for silly mistakes in there, but not too bad if you can avoid those. On to question 6. The ellipse E has equation this, so A is 5, B is 3. The line L is normal to E at the point P, where theta is between 0 and pi by 2. Put a little diagram here. Here's our ellipse. Between 0 and pi by 2 puts it in the first quadrant, let's say here. This is 5 cos theta, 3 sine theta. Part A, using calculus, show that an equation for L is that. Okay, we've got our equation, x squared over 25 plus y squared over 9 equals 1. We're going to differentiate that to find the gradient. Use m1, m2 equals minus 1 to find the gradient of the normal, and then use the point given to find the equation. Differentiating this, you can do this in different ways. You could use dy by d theta divided by dx by d theta, but I'm going to use implicit differentiation this time. 2x over 25 plus 2y dy by dx over 9 equals 0. Rearrange. Dy by dx is equal to minus 2x over 25 times 9 over 2y. Cancels with that. Minus 9x over 25y. And then at the top of the screen there, we've got the x and the y for point P. So that's minus 9 times x. 45 cos theta. And 25 times 3 sine theta. 75 sine theta. And that is the gradient of the tangent. For the gradient of the normal, we flip that upside down and make it negative, or in this case positive, because it's already negative. Oh, why have I still got those big numbers? That takes it back to a 5 and a 3. There we go. Now using one of our line equations, in this case I will do y minus y1 equals mx minus x1, where x1 and y1 are the points we've already used in finding the gradient. That's y minus the y coordinate was 3 sine theta. The m that we just found, 5 sine theta over 3 cos theta times x minus 5 cos theta, the x coordinate of P. Multiply everything by 3 cos theta, and I'll expand that bracket. That gives us 3y cos theta minus 9 sine theta cos theta is equal to 5x sine theta minus 25 sine theta cos theta. And then just rearrange. Do they want the x or the y positive? The x. So 5x sine theta. Bring the y over, minus 3y cos theta. And put the others on the other side, gives me a positive 16 sine theta cos theta. That should match. Yes. Given that L intersects the y-axis at the point Q, so back to my diagram here, L is perpendicular, so it's coming through, it's the normal to the curve. Cuts the y-axis at point Q. The midpoint of the line segment PQ is M, okay. Determine the exact maximum area of triangle OMP as theta varies, where O is the origin. Oh dear. We've suddenly gone from fairly standard questions to a fairly horrible question. You must justify your answer. Well, I take that to mean show your process. So we want OMP. This little triangle here. Oh, that's horrible. How do we get that? Okay, jumping up to the top of the screen here, I'm just going to note that theta is between 0 and pi by 2. So it is only in that first quadrant. Obviously when theta equals 0, there is not going to be any triangle. The area will be 0 because P will be on the x-axis and L going through as a normal will be the x-axis. So there won't be any triangle. Similarly, when it's pi by 2 up here, P will be on the y-axis, same argument. M will also be on the y-axis because the line will be on the y-axis and there'll be no triangle. So it's somewhere in between. I've just realized I didn't need to go through all that because it doesn't even have an equal sign here. It's between these two values. It's not equal to. Never mind, it doesn't hurt to think it through. How do we actually find that area? If we know M is the midpoint, give me a second and I will draw it out. This usually helps me. We've got O, Q, P. M is here. So that's half. And if we know O to Q and times that by this distance here, which we know that's the x-coordinate of P, that's 5 cos theta. So the area of OPQ is OQ times 5 cos theta over 2. Therefore the area of OPM is half of that. So that's OQ times 5 cos theta over 4. So we need to know the distance OQ. The distance OQ is just the magnitude of the y-coordinate of Q. So we need to find where the line L intersects the y-axis. That is when x equals 0. I'll pull all of that down here. And we can find the y-coordinate of Q by putting x equals 0 into this equation here. That gives us a 0 minus 3y cos theta equals 16 sine theta cos theta. We know cos theta can't equal 0 because we've got theta between 0 and pi by 2, not equal to. So I can cancel those two without worrying about dividing by a 0 by accident. So minus 16 over 3 sine theta equals y. So OQ is the magnitude of that, 16 over 3 sine theta. So the area of OPM is 16 over 3 sine theta times 5 cos theta divided by 4. Just put that there like that. That's 20 over 3 sine theta cos theta. How do we maximize that? We want the maximum area as theta varies. We could differentiate that. Don't want both functions. Let's make that a sine 2 theta by pulling out a 2 like that. Make that really clear where that's come from. And then if we differentiate that, we get 10 over 3 times 2. Oh, I don't think we need to. You could do it that way. And if I weren't in the middle of problem solving a slightly unusual question, I would just automatically do that. But you don't need to because we're maximizing this. The maximum value of sine 2 theta is a 1. It will always be a 1. And that happens when theta is equal to pi by 2, which it can't be, but it isn't actually theta, it's 2 theta. So when 2 theta equals pi by 2, this will be a maximum. Sine 2 theta will be a 1. So I can just say the maximum area is equal to 10 over 3. That happens when sine 2 theta equals a 1, which is when theta equals pi by 4. But I don't need any of that. I just need the 10 over 3, I think. It says you must justify your answer. Let me put a little something there. Max at 2 theta equals that because sine 2 theta equals sine pi by 2 equals a 1. I think that would be good enough. Moving on, that was a much more involved question. Question 7. Figure 1 shows the curve with the equation log of tanh x over 2 shows that the length s of the curve is given by a fairly simple integral. Okay, we're differentiating, so we've got y is equal to log of tangent x over 2, and I say we're differentiating because of the formula for the arc length. This is in the formula booklet, and it's the integral of the square root of 1 plus dy by dx squared dx, and we're going from 1 to 2. So although we're integrating overall to get that arc length, we're differentiating to figure out what that integral has to be. Now over here, let me note the derivative of log x, of course, is 1 over x, but if you've got a function, it's the derivative divided by the function, and that's dy by dx. So we're going to have to differentiate tangent x over 2 and that hopefully is in the formula booklet. Yes, here it is. Tangent differentiates to sec squared x. So that's sec squared x over 2 times by a half. So this is a bit messy, but taking this down here, dy by dx for that is equal to the derivative of the function in the log. So that's a half sec squared x over 2 divided by the function itself, tangent x over 2. Now that doesn't look too bad, except we need to make it look like coth x in the end. Now I'm quite happy to admit that this is not the first time I've done this question. The first time I did this question I really struggled because I did not read the question carefully enough. I was using x over 2 to try to get coth of x over 2, which you can't do, it doesn't work. And it took me a long time to realize that I had misread and it was just an x here. Or not misread, I just hadn't even stopped to read it slowly and carefully. So I spent far too long trying to figure out how this worked, when what I should have been doing was looking for a way to change x over 2 into x. And the easiest way, once you realize that, of course, the easiest way to do that is with sinh 2x, 2 sinh x, cosh x. And we can get sinh and cosh out of this because that's what tangent is, and sec is 1 over cosh, so I'm going to put all of these in terms of sinh and cosh. So we get a half, well, let me do it more sensibly. Our tangent is sinh x over 2 over cosh x over 2, and the half has that 2 on the bottom. And then the sec squared is a cosh squared down here, and that cancels with that, and then we have got exactly what we need. 2 sinh x over 2 cosh x over 2 gives us sinh 2 of x over 2, which is just sinh x. I spent ages trying to figure this out, and when I realized the mistake I'd made, it was quite straightforward by comparison to all the things I was trying. So a quick side note there, very important to read the question. But we're still not there yet, we need to get coth x, not 1 over sinh x, and that's because I haven't put it into the integral yet. So s is equal to the integral of 1 plus 1 over sinh x, which is cosec x squared, square rooted. And 1 plus cosec is coth squared. 1 plus cosec squared x equals coth squared x. So at this point it just naturally falls out of the situation. We've got this, which gives us coth x, not x over 2. And our limits are still 1 to 2. And there we go. Part A, easier than I thought it was first time round. Hence, show that s is equal to this, so we're just going ahead and integrating. Back to the formula booklet. Now, I've mentioned this on a previous video. There are certain functions that are not here, but which you can kind of remember by going back to the FP3 section. And this is where I look first of all, but this doesn't help in this case because we're not differentiating coth, we're integrating. So I go down to the integration bit, and this isn't something that I've got in my mind that this is definitely going to work. But if I put an h there and make that coth, log of sinh might be the integration that I want. So that's where I'm going to start. So what I'm going to do on the side is start with log of sinh x, differentiate that, and see if I get coth. And if I do, then I can integrate back to this. So as with what we had previously, differentiate the log, you get the function in the denominator and the derivative of the function, which in this case is cosh, and that is 1 over tench, which is coth. So that's correct. Integrating this will give me log of sinh x from 1 to 2. Putting that in here, log of sinh 2 minus log sinh 1 is not how we needed it. We need e plus 1 over e. Okay, there's a bit of simplifying somewhere in here. So I'm going to put in 2 here and a 1 here. And then because of the log rules, we can divide those. When we divide those, the 2's cancel out, and I get this. And if you'd like to chuckle at my misfortune, I'll let you know that I also spent ages on this question. I misread the 2 as a 3, and if you do that, you can't make this look like it's supposed to look. It doesn't work. And I tried and tried, and a little tip here, if you get something like that where you're trying to simplify something to make it look like something else, and you're not sure what's going on, just put both things on your calculator and make sure that they do actually match in decimal format. That's how I realized that I'd done something terribly wrong, and it was a 2, not a 3. So I know exactly where we're going with this because I've already done it. This is e to the 1 plus e to the minus 1 times e to the 1 minus e to the minus 1. Difference of 2 squares on the top there, and then they cancel. And that gives us log of e plus e to the minus 1, which is e plus 1 over e, as required. Not too bad a question if you read it properly. And if you don't, it will make you very frustrated. Question number 8. We've been given in is equal to this integral here, where k is a positive constant. Show that this is true. Okay, this is a fairly standard looking reduction formula. X to the n, k minus x to the half. So unless it's fairly obvious to do otherwise, integration by parts is my usual starting point for a question like this. The integral of u v prime is equal to uv minus the integral of vu prime. That's in the formula booklet if you need it. And here I'm going to be wanting to differentiate this because I can see an n minus 1 here. That's the easiest way I'm going to get that out of this. And this bracket with the power half, we're going to integrate that. So over here, that becomes nx to the n minus 1. And integrating that will give me something like this. But if I differentiate this, I get a 3 over 2, which I don't want. And I'll get a minus out of that bracket as well, which I don't want. So minus 2/3 should take care of those. Now I'll put those into the integration by parts formula. U times v, so that's x to the n times minus 2/3 k minus x to the 3 over 2. That needs the limits applied, and then minus the integral of v times u prime. So n, oh I don't want brackets forever, let's have a plus 2 n over 3 x to the n minus 1, k minus x to the 3 over 2, like that. Try and simplify these limits first. We get k in here. Oh, that's nice. That makes a 0 in that inner bracket. So everything is 0. And the 0 in the x to the n makes a 0. That whole thing is 0. 0 minus 0, if I write it in my usual way. Plus, now what's going on over here? What we need is a power half on the bracket in order for the I notation to come back in. So I'm going to split this power into a whole bracket and a half bracket. Then that whole bracket, I can just multiply that bracket out. That often is what happens with these questions. We've got k minus x times k minus x to the half. Leave that second bracket alone, but multiply out this first bracket to give us two big terms. So if I multiply out with the k, that gives us 2nk over 3x to the n minus 1 with that second bracket. Now with the x, we get minus 2n no k, and the x multiplies with the x to the n minus 1 to give x to the n. The 3 is still there, and we still have this bracket on this term as well. Now this is looking pretty good because we've got the format of the original in on both of these terms. So this first term is 2nk over 3 lots of I n minus 1, and the second term is 2n over 3 lots of I n, and this equals in. Now we just need to rearrange, so the in's come together. We get in plus 2n over 3 in, make that a 3 over 3, factorize out the in, 3 plus 2n over 3, that still has to equal 2nk over 3 in minus 1 on the other side. Divide through by the bracket, actually the 3's cancel. Divide through by the bracket, and we get 2nk over 3 plus 2n lots of in minus 1, and hopefully that matches. 2nk, 3 plus 2n, yes. Part B, given that this thing with a 2 here, so n equals 2, is equal to 9 root 3 over 280, determine the exact value of k. So I2 equals 9 root 3 over 280. And we know I2 because we can put 2 in here. So I2 is equal to 2 times n is 2, so that's 4k. N is still 2, so that's a 7 times I1. And then we can do the same with I1, so we've got 4k over 7 times this thing with n equals 1, so that's 2 times 1k over 3 plus 2 times 1, 5, I0. And then we can't do this with I0 because we don't want to get into I negative 1. We haven't really defined it for that, but we can put 0 back in the original, which makes our x to the 0 a 1, and we just get k minus x to the half. So that equals 8k squared over 35 integral 0 to k of k minus x to the half, which we've already integrated as part of our process here. So that's minus 2/3 k minus x to the 3 over 2 from 0 to k, and if you put a k in there, that is 0. So applying our limits, we get 0 minus 2/3 times k minus 0 to k to the 3 over 2. There's a lot of powers going on here. That's 16 over 105 k to the power 2 plus 3 over 2 is 7 over 2. And all of that has to equal the thing at the top there, 9 root 3 over 280. What does it say about k? The exact value. Okay, that suggests it might be a third. So does the fact that there's a third already there. Rearranging that fraction on the left to the right gives me 27 root 3 over 128. Squaring that and then taking the 7th root on my calculator gives me the surprisingly nice answer of 3 over 4. After all of that, there was no third, assuming that's the correct answer. And was that the end? That was the end. Okay. On to the final question, question number 9. The plane pi1 has vector equation this, where s and t are scalar parameters. Determine a Cartesian equation for pi1. Okay, a Cartesian equation, we're going to be using r dot n equals a dot n, so we need the normal equation. A can be the point given, that's no problem. 5, 3, 0. And then to get a normal equation, we're going to cross the two vectors that we know are in the plane, i.e. the two direction vectors given in the vector equation. 3, 0, 1 crossed with 1 minus 2, 2. My little fish system gives me a 0 minus minus 2 is a 2. 1 minus 6 is minus 5. And minus 6 minus 0 minus 6. So r dot 2 minus 5 minus 6 is equal to 530 dot 2 minus 5 minus 6, which is equal to 5 times 2, 10, plus minus 15, plus 0 is a minus 5. That's still not a Cartesian equation. Turn this into the general x, y, z, and do the dot product on this side. Gives us 2x minus 5y minus 6z is equal to the minus 5 we found on the right. That's our Cartesian equation for plane pi1. Now we're told the plane pi2 has vector equation this. Determine a vector equation for the line of intersection, giving our answer in this form here. Okay, if we've got two intersecting planes, if I can try to draw these, excuse the bad drawing, like so, kind of, and this is the line of intersection here, and the direction vector of that line must be in both planes, i.e. perpendicular to both normals. So to get that direction vector, I cross the two normal vectors of the planes. We found the one we need for plane 1 in part A, and we're given the one for plane 2 here in part B. So 5 minus 2, 3, crossed with the one from plane 1, 2 minus 5 minus 6. And this will give us the direction vector for the line of intersection. Minus 15 minus 12 is minus 27. Minus 30 minus 6 is minus 36. And then minus 4 minus minus 25, 21. And we don't need all of those. We can pull a 3 out of that. You don't have to, but you can. I prefer the smaller numbers because we just need the direction, not the numerical values that we necessarily get out of that. So I'm going to use minus 9, minus 12, and 7 as the direction vector. But we also need a point on that line. And that means we need a point that is on both planes. For the Cartesian equation that we've got here, the point needs to satisfy that. It also needs to satisfy this equation equals 1. And the way I would normally do this is to say, almost certainly, somewhere on this line, there's a point where x equals 0. And if there isn't, if that happens not to work out, then definitely there will be a point where y equals 0. But I tend to like to start with x equals 0. So what I'm going to do is say let x equals 0 And almost certainly, or if not this, then definitely y equals 0, one of these will work. So if I say if x is equal to 0, then the equation we've got on the screen there, that makes plane pi 1 minus 5y minus 6z. That still has to equal minus 5. And at that same point, this other equation, that's 5x minus 2y plus 3z equals 1. This is pi 2. This is pi 1. So assuming there is a point on both of them where x equals 0, then that would make this equation for pi 2 minus 2y plus 3z equals 1. Now there's no guarantee that this will work, but it almost certainly will. And if it doesn't, then it's certain that y equals 0 will. So I just solve these simultaneously now to find the y and z coordinate where this is true. To do that, I'll double this. 4y, 6z equals 2, and then add them together. We get minus 9y equals minus 3. Y equals 1/3. And if y equals 1/3, putting that back into one of the equations there, we get minus 2/3 plus 3z equals 1. 3z is equal to 5 over 3. Z is equal to 5 over 9. So it's worked out. We've got a coordinate for y and z. So the point 0, 1/3, 5/9 is in both planes. So my A vector is 0, 1/3, 5/9, and I can put that together with my B vector, minus 9, minus 12, 7. And any old parameter that we like, unless we were told. I think we were actually. It had a certain format. What was the format? R equals A plus lambda B. And this is the equation for the line of intersection. Now if you did this question and got something that looks very different, it might still be right. There's going to be a lot of different answers. You could have any multiple of this direction vector and any number of points that would be on this line. That's one I'm confident that will be in the mark scheme though, because of the way that I've done it. It's fairly standard. The mark scheme probably has one for y equals 0 and also one for z equals 0. Moving on to finish the question, the plane pi 3 has a Cartesian equation 4x minus 3y minus z equals 0. Use the answer to part B to determine the coordinates of the point of intersection of all three planes. Now we don't need all three planes because we've just found the line of intersection of the first two, so we just need the line equation and this plane equation here. Where do they intersect? 4x minus 3y minus z. Equals 0. This is part C. So I'll use the general point, the line equation above. We've got 0 plus minus 9 lambda, 1/3 minus 12 lambda, and 5/9 plus 7 lambda. And I'm going to put this into the plane equation. 4 minus 3 minus 1 x, y, z has to equal 0, changing into that format there, putting this in here, doing the dot product, making it equal to 0, and calculating what is lambda. I've been a little bit lazy there and copied that. So this is the dot product that I'm doing. Minus 9 times 4 minus 36 lambda. And we get minus 1 plus 36 lambda, that's nice. And then minus 5/9 and minus 7 lambda equals 0. So minus 7 lambda is equal to 1 plus 5/9, that's 14/9. So lambda is equal to minus 2 over 9. Now we put that back into the R equation, this thing here, copied from above, and we just substitute in lambda equals minus 2 over 9. So we get 2, a 3, and a minus 1. Very nice numbers in the end. So the point of intersection, the coordinates are 2, 3, minus 1. That's the end of the question and the end of the paper. Again, we've hit the final page. I hope that has been helpful for you.